Okay, next is the second talk of the second day, and this will be given by Jnawali, and he'll be speaking about Mira stars as distance indicators.
Thank you very much. Today I am going to talk about a Mira star, and why I choose the object is a basic point I want to say. Mira star is a Mira star. Mira means a wonderful. And to enter into the astrophysics to look at different field like the mass rate, to study the different wavelength variation in the star, how stellar evolution happen. All of this information can be obtained from the Mira star, and it is still an interesting object to all of us because a lot of research is going on it, and I am trying to do my work Mira as a distance indicator. And for this I need an introductions, what is Mira star, and then I will classify the Mira star. And Mira star is a type of variable star. And variable star is very important in other aspect. And then I will talk about physics of pulsation, what causes it to pulsate. Then I am talking about variable star. Why should we care? That is also important when you are doing a research. And my goal is to calculate the distance to Mira star. And then data I got data from the AAVSO, that is very good organization for us to work on the variable star. And then calculations, results, and with future work. Then this is a Omicron Ceti, and Omicron Ceti is a Mira star. If we are talking about only Mira, then we can assume it is a Omicron Ceti. And before going to that part, I think we should know about the HR diagram. Why HR diagram is important, and it is a basic and summarized form of the different stars and how their evolution is going on, which star is lying in which part, and we see that there is a main diagonal line, that is a main sequence line. And I am talking about the Mira star that is just above that line. Now,
Oh, could you go back? Come on. Can you point to where Mira is?
this part.
Okay.
And then Mira is a red giant star constellation Cetus, and it is discovered by the Fabricius. I already talked that Mira means the wonderful star, and its radius is far more greater than the radius of the sun, but mass is similar to the mass of the sun. And Omicron Ceti is the oldest known Mira star. And what is variable star? If the brightness changes periodically, then we call it as a variable star. And what important aspect of the variable star is that if a star has a lower temperature, then it can show the variability in its brightness. And classifications of the variable star. There is two, intrinsic and extrinsic variable star. And intrinsic we can classify into eruptive star and pulsating star. And eruptive star is, we can give an example of supernova. And for the pulsating star, I am talking about Mira star over here. And there is one interesting about the eclipsing binary star. This changes its magnitude when some other star block it. When we are looking it on the line of sight of observations. In rotating star, that is because of the some patches, some roughness in the surface of the star. Now this is the figure from the Chandra Harvard video. I just took it from the website. And this is the pulsation of the Myra star, how it is going to change with the color. And then I will talk about the pulsation of the Myra star. There is a lot of assumption is made to identify the pulsation of the Myra star. Still, research is going on. But I am talking about the three important physics behind the pulsation that is currently known. We know the Kappa mechanism is related with the density of the particles and the temperature. And in one attempt, if we look on the compressed state, then we should assume that the opacity should be decreased because we have low temperature. No. If we have low temperature, then we assume opacity is increased.
I have a question.
Yes.
What is T in that equation?
T is a temperature.
Which temperature?
Temperature due to the.
Is it the central temperature? Is it the surface temperature, or the temperature? 4 pi r squared sigma T to the 4th.
This is the temperature because when something is going down, the nuclear reaction heating up, that produces this temperature.
Is it the temperature in the center of the star, or where the optical depth is 1, the Rosalind temperature, or is it the surface temperature? Where in the star?
This is just below the surface, not on the surface.
Oh.
Below the surface, this temperature.
And the density is in the same place, right?
Yes, density on the same line.
Okay, thanks.
And we can see that if we have minimum temperature, then K goes more. If we have maximum temperature, K goes less. So when we are assuming the compressions, we should expect K goes down. But that is not going to happen to the Myra star. Because of the ionized state of the helium. And in that case, what happened when the star is compressing, the helium atom plus helium atom is going to form in rapid way. That trap the more light because opacity of the helium plus is more. Why? Because helium plus is more unstable than the helium plus. So that causes trapping of the light more. And that causes increase in the temperature of the star. Because of that, we know from the thermodynamics, if something has more temperature, then we try to expand. At the same time, opacity is going to down and let photon get out. So that is the main idea behind the K mechanism. So do you have any questions on this part? Okay. Then there is another model which assumes the pulsation mode. And in this, I took these equations directly, and there is a relations with the change in the radius of the star. And we need some pressure, like a pressure, we need another equations for the density and radius. And in order to solve any equation, we need a boundary conditions. And choosing a boundary condition makes your solution more good. So what boundary condition you might expect. Generally, boundary condition is calculated at one point at the center, another point on the surface. And we can expect there is a fundamental mode, first order tone, that is related with sound wave. In sound wave, fundamental mode is like this wave. Because we have two nodes. And in the same way, we can expect the first order tone. But we could not expect second, third for the Myra star, because Myra star has a more pulsating period. If you need more pulsation, you should go up to first over two, not to second, third, fourth. However, it is difficult for us to calculate this mode also. And in the Myra star, we expect it should be a fundamental mode because it's give the more period compared to the first mode. So that is the most assumed model for us for the Myra to determine why Myra is going to pulsate. There is thermodynamics and relativity theory for the pulsations of the Myra star, and that is basically related with the idea of the entropy. Entropy, if you go from one side to another side and return back to same, in the same way, at that time the entropy should be zero. But in the Myra star, we can expect there will be some fluctuations, but still we assume it as the process going on the Myra star should be reversible one. Because of that, it pulsates like this way, and we can derive these things that if we absorb it, we have more temperature. If we lose it, we have less temperature. So that is all about the thermodynamics. And why should we care to the variable star? We should care because we can calculate the distance. We can look on the stellar evolutions of the star. And mass and age are fundamental properties that we can see from the HR diagram. And mass can be calculated from the luminosity. And that we can get from the brightness. And that we can get from the distance. And distance we can get from the Myra star as a distance indicator. So this is a process of stellar evolutions. Myra star, in future, sun will go to the Myra star. So it should be better for us to read some about Myra star. And it will finally goes to planetary nebulae and then to white dwarf. And Myra star, this is my target star, of which I am going to calculate the distance. And there is a RCB, eruptive variable star, that is very important for us because it is good for the dust formations in the sky. And that is the plot I got. For this, I choose data from the ALSO. And what I see, you can see here, most of the time the star lies at the magnitude of the 6. But why there is sudden drop of the magnitude? Because it just emits the mass, its mass from the star that causes the light to redden. And that is very good to study in the infrared band. Visible band is not good for this case because dust particle, if we are going to study on the dust particle, we should work on the infrared band. So the goal of me is to calculate the distance, and I calculate it through the period luminosity relations. The relations is given by the Henrietta Swan Leavitt for the Cepheid variable star. and then what will be the distance to Myra. I will talk about these things. Most of the research is going on the infrared band, but I got data from the visual band. So it is little bit difficult for me to find the data to calculate the absolute magnitude relationship with the time period to the star to calculate the absolute magnitude. So when I plot this data to get a best fit line, I could not get an exact result, the relation between the absolute magnitude and time. So I choose a paper, and from this paper I choose absolute magnitude equals these relations. And obviously American Association of the Variable Star Observations is a source of me to get a data, and I am working on the visual band. And one important thing is that AAVSO supports us. If you want to study some variable star, then they can provide telescope to take a data, and you can submit your data to them. So one interesting figure over here is that we see that each curve is not going to appear same at the different time. Why this is happening? Because of the rate of loss of mass from the Myra star. That is the main points for it. And second, the metallicity of the star, that also causes this. And then apparent magnitude will be the average, and that will give us that value, absolute magnitude time period. And then D is, I got 411 light year, 126 parsec. And then I could compare my result with Rai data. Those papers got 128 parsec. And my future work is that I will try to look it on the infrared band, because it will give more exact relations and it is more flat. And attenuation in the visual band is more, that we already understand. So calculating the distance to the Omicron city based on the infrared band observations and working in the infrared band, we can get tremendous amount of information like mass, loss rate, description of the dust around the star. So that is the picture I got, and in that picture we can see that there is a tail of the Myra star. Myra star is still Myra. Thank you.
Okay, questions? Anyone? Let's see. Could you go back about 5 slides? Yeah, that's good. Go forward. Forward, not back. Go forward.
Forward?
Forward. Keep going forward.
Yes, please.
Keep going until I tell you to stop. Okay, stop right there. What are those dots on that plot?
I just try to get a best fit line.
What are those dots? What are the
These
dots?
dot are the star with their absolute magnitude.
Where did you get the information?
I got this information from the Bark, our research paper, where we have only 9 stars.
And so go back to the slide. Okay, so you got information from the Sydney Vandenberg paper,
Yes, but.
and you got the information from there, and you made a plot,
Yes,
and then you fit a line to it.
yes,
And your best fit line is represented by that equation, right?
Yes.
Now go to the next slide. Where did you find that equation?
in that equations, he mentioned that,
Hold on. Where did you find that equation?
where,
Yeah, where did you read that? Did you read that equation?
yes,
Where did you read it?
I read it from the Barak Bandit,
So he has that equation.
yes.
And does he use the same 9 stars that were used in your previous plot?
He used the same line with the accurations.
Hold on. Did he use the same 9 stars as the
Yes,
lines?
yes, he
Yeah,
used
did.
the same line.
Same data.
Same data, but this data is not going to support for his star also. So he made some corrections.
Uh-huh. Is Myra included in this data set?
Yes, offset is included.
So you're using a relationship that includes the star that you're trying to study,
Yes,
and you get a distance that's the same as what's published for the star.
yes. I am trying to gauge.
Interesting.
Because we know that the magnitude, absolute magnitude also changes. So,
I would have thought that you would have wanted to use a relationship from a bunch of other stars and then use that to estimate the distance to the target star, and then compare that distance to an independent measure of the distance to see if the relation predicts the kind of distance that you measure with another method.
what will happen is that there is still work is going to set the relation between the magnitude and time period, because this is going to change continuously, and we need our equations that will satisfy by the other star also, based on this observation. Because if we pulsate the star, its absolute magnitude is going to change. We are looking at the time period at which all stars going to maintain one conditions. So that condition will be valid for other stars also.
Do you know if anyone has estimated the distance using a different method for this star?
This right calculate this distance by different method.
Yeah, has anyone done that?
Most of the research is going to calculate the absolute magnitude relations with the time period.
Or has anyone else estimated the distance for this star using a different method?
Like other method is there, yes, Hipparchus.
Hipparchus estimated the distance?
Hipparchus method,
Hipparchus estimated a distance for this star?
yes.
Whereas that's 400 light years, it's kind of far for Hipparchus, right? But it was okay?
Yes, but some of the research, some of other author calculate the distance up to 350 light year.
Oh.
So at that point I could not say. Some of them got 320.
So what was when you say 320, that was using Hipparchus?
Different research paper using different step, but I could not say other method for this. But distance is significantly different from different, because the loss of mass rate, there is rate of loss of the Myra star continuously happening, and that is moving toward us, or because loss of rate is strongly related with the time period and absolute magnitude. That is also going to change the absolute period line relationship.
Anyone else have any questions for Kamal? Let me take a quick look because I thought I had one other question. Oh, I was just curious. You had a few slides on our Corona Borealis.
Yes, I took this star because it will help us to study the dust formations, how dust form in
Could you go back to the slide on our corona borealis? Right there, yeah. Then go to the next slide. Is this is an erupting system? Is that
the,
right?
this is erupting.
And what is the cause of the drop in the light?
That is because of the dust that is going out from the star, and that is carbon, that dust is carbon rich, and that is going to redden the light. So this causes to drop of the magnitude like this.
And then the magnitude, it comes back up.
Yes.
So why is that?
Because this dust is going to disperse after some time.
So it gets thinner,
Yes.
and then you can see the star
Yes.
again. And then there's some more dust.
Yes, that is really.
Okay, is that it? No more questions? Let's thank Kamal again.